Okay, welcome back. So this is P12, which is magnetism and the motor effect. Really interesting topic. If you haven't already, please make sure you've watched the P10 video, which talks about current, because we're going to be revisiting that concept in this lesson. So let's start off with magnets. So you should know from primary school, okay, that like poles, so a north and a north, or a south and a south, they will repel, they will move away from each other, and opposite poles, so a north and a south and a south and a north, will attract, okay? So very similar to the P11 topic where we talked about the charges, opposites attract and like charges repel, okay? So, what are some uses of magnets? Well, compasses, phone cases, locks, and even lifting, objects in a scrapyard. So just make sure you're able to list some uses of magnets, okay, in your exam. What is meant by magnetic material? Well, it is a material that will be attracted to a magnet, okay, that's the definition. There are three magnetic elements you need to be aware of. They are iron, nickel, and cobalt, okay? So, you could be asked in your exam, name a magnetic element, and you just need to name one of them, okay? So what is the difference between a permanent and an induced magnet? Well, a permanent magnet, as the name suggests, it is permanent. It will always be a magnet. Whereas an induced magnet is obviously, its magnetic properties can be taken away from it, okay? So it can be turned on and off, essentially. Right. Now remember we talked about electric field lines in my previous video. With magnetic field lines, it follows a pretty similar. It's pretty similar to electric fields. You just need to know that magnetic field lines always go from the north pole of a magnet to the south pole. Okay, and they follow this curved line pattern like you see here. Okay, so we can have what we call a magnetic field around a bar magnet, okay, or what we call a uniform magnetic field, okay. So a uniform magnetic field is essentially when the magnetic field lines are parallel, like you see in this diagram, okay. So if we look at this bar magnet and we look at the magnetic field lines, they're the most concentrated around the poles, so that's where they are the strongest, where the magnetic field's the strongest. And where are they the least concentrated? Well, they are least concentrated the further out they are, the further they are from the bar magnet, okay? That's because magnetic field lines cancel each other out at the top and the bottom, okay? The further out they are from the bar magnet, okay? Okay, another common exam question is essentially how do you use plotting compasses to find the shape of a magnetic field around a bar magnet? Okay, so here's our bar magnet, and essentially if we put our plotting compasses just randomly, okay, around the bar magnet, we will know that its needle will literally eventually become stationary, so it will stop spinning, and when it does, all you need to do is with a pencil on either end, okay, just draw a dot there, draw another dot there, and then you just move your plotting compass to another position, okay, let's say over here. Okay, same thing, draw a dot there, okay, at one end of the needle and then at the other end of the needle. As you place that plotting, and obviously you continue this process for a number of points around your bar magnet, then all you need to do is then connect up the dots, because eventually you will find a single line, okay? So if we move this compass over here, we would see that it would follow this line here, okay? And eventually, we can begin to draw a picture of the magnetic field lines around the bar magnet. Okay, so just make sure you're able to describe this process in your exam. So, explain how compasses work and why the core of the Earth must be magnetic. Well, compasses are made from magnetic materials and they line up with the Earth's magnetic field. Okay, so we know that the inside of the Earth must be magnetic. Otherwise there would not be a magnetic field being generated, and as a consequence, in the same way that compasses will point towards the north pole of the magnetic of a bar magnet, the same thing will occur with the Earth. Okay, so you can imagine the Earth as one huge bar magnet inside. Okay, right. When a current flows in a long straight wire, it creates a magnetic field. So, how I tell students, I tell my students that this is the right-hand screwdriver rule. So if you imagine, here's my cursor here, the magnetic field, sorry, the current is coming out of your screen, okay, into your eyes, okay? Now, if with your thumb, okay, and this has got to be your right hand, and you place your thumb pointing towards you, okay, the direction, the rest of your fingers, and keep the rest of your fingers slightly above the palm of your hand, the rest of your fingers are going to twirl anti-clockwise, okay, kind of like these concentric lines you see here, okay? Do the same thing over here. Now this cross sign here means the current is going into the screen. So with your right hand, literally move your thumb so that it is pointing the screen, and then you should see that the rest of your fingers should make a clockwise motion, okay? And that is the direction that these concentric lines around this current going into your screen are making. Okay, so that's how you can remember it. Okay, so a common exam question is when they ask you, how do you reverse the direction of the magnetic field? Well, if we know that current is going one direction, so in this case it's coming out of the screen, well, all we need to do is just reverse the direction of the current, and then the magnetic field lines will also change direction, okay? The strength of the magnetic field does depend on the current and the distance from the wire, okay, where the current is flowing. So as we can see, the magnetic fields are more concentrated closer to the wire here, as opposed to the further out they are from it. And also, I mean, if we actually increase the amount of charged particles moving through that wire, we would also generate a larger magnetic field. Okay, so it's all in proportion with the current in the wire. Okay, so we can create an electromagnet, or what we call a solenoid, by sending a current through a coil. Okay, and what that creates, essentially, we will create a strong uniform magnetic field inside the coil. Okay, but outside the coil we will get a weaker field, because the field lines at the top and bottom of the solenoid or electromagnet will cancel out. Okay, so essentially, I know this is a bar magnet, but the same magnetic field lines will be generated if you imagine this bar magnet as literally a coil of wire. You would generate these same magnetic field lines, and the strongest the magnetic field will be inside the center of that coil of wire, and again the weakest that it will be the further out, okay, because you're going to get field lines from the top cancelling out with field lines from the bottom, and so that's why you get weaker field lines, okay, and when the magnetic field lines go in opposite directions, they cancel each other out, okay.